Now, kids, this is where things get really fun. So far, we've looked at DIS, the domain, the intercepts, and the symmetry of a function. Now we're going to look at VARD, which is two things. VA stands for vertical asymptotes. Notice the fun spelling. You need to know that. And RD stands for removable discontinuities. A function can have as many as you want of either of these things. Let's focus on the vertical asymptotes, but both vertical asymptotes and removable discontinuities. To find them, you need to simplify. You need to simplify your rational function. So let's start with R3, for example, on your homework sheet. It was given as x squared plus 3x minus 10 over x squared plus 8x plus 15. Let's go for the vertical asymptotes. Let's simplify this thing and then identify where the vertical asymptotes are. First of all, a vertical asymptote is going to be a vertical line that the function cannot cross and gets really, really close to. So a vertical asymptote might result in a function looking like this. The function might go off and do something fun over here, it might do something fun over here, but this vertical asymptote, let's say it was x equals 2, we would say there's a vertical asymptote at x equals 2. There's not necessarily a vertical asymptote at x equals 2 in this function, but if there was, this is what it would look like. It could either go up on this side, or it could go down and up like this, or both up and both down. We'll get to that later. So that's what a vertical asymptote looks like. Let's find out if this function has any. So the first thing you need to do is factor if you can. In this case, you can factor. The numerator turns into x plus 5 times x minus 2, and the denominator turns into x plus 3 times x plus 5. You'll notice that there's a common factor on the top and bottom, the x plus 5 and the x plus 5, leaving you with x minus 2 over x plus 3. In simplified form, most simplified form, you can't go any further with this, look at the domain of the simplified form. The domain of the simplified form, x cannot equal negative 3. That means there is a vertical asymptote at x equals negative 3. So after you simplify, look at the domain of the simplified function. Wherever the holes are, that's where the vertical asymptotes lie. Look at the term we crossed out. We crossed out the x plus 5s. What was the domain if we hadn't crossed out the x plus 5? The domain of the original function, which is the domain of the function we started with, x can't be negative 3. It also can't be negative 5. What's going on here is that the top and bottom, that behavior was canceled out of the top and bottom. What that means is, functionally, when you look at this graph, it'll look like nothing has changed, except whatever this function does, it's going to be traveling along. Wherever it hits x equals negative 5, there's going to be an open dot there, meaning the function can get infinitely close to negative 5, but it can't actually equal x equals negative 5. So wherever the function crosses the x value x equals negative 5, there's an open dot. Now you might ask yourself, where does that open dot actually occur? Well, in this case, this function right here is almost equivalent to this original function, except we've taken the removable discontinuity out. We have filled it in. So let's find out where that would be by looking at the simplified form. If we take the simplified form, so you can think of this R3 simplified of x was x minus 2 over x plus 3. Let's plug in 5, and end up with 5 minus 2 over 5 plus 3 equals 3 over 8. You actually find out that this point on this particular, for this particular rational function, there's an open dot, and that open dot occurs at negative 5 comma 3/8. So there's an open dot there, not a vertical asymptote. So once again, to find the vertical asymptotes, you need to fully simplify your rational function and look at the domain of the fully simplified form of the original rational function. In this case, the original rational function simplifies down to x minus 2 over x plus 3, which has a domain of x cannot be negative 3, x such that x cannot be negative 3, meaning there is a vertical asymptote there. So far you have disvard. So we have domain intercepts, symmetry, vertical asymptotes, and notice the spelling, asymptotes, and you can have more than one, and you have removable discontinuities. The key difference between these two right here is that much more warping goes on with vertical asymptotes. Wherever there's a vertical asymptote, there's this dotted line that actually isn't on the graph, and around it the function's either going to go like this, or it's going to go like this, or this, or this. The key to it all, though, to finding both, is you must simplify. And this came up in class. You guys are fine with quadratics. Solving things like that, you're pretty good at it. Your failsafe is always the quadratic equation. You know how to use that. But what happens if, let's say, you needed to work with x cubed plus 7x squared plus 7x minus 15? This is a cubic, and this is where things get really fun. Because I love factoring, and so will you. The problem with factoring higher degree polynomials is you can't just do it with guess and check. There's sometimes way too many things to guess and check. We are trying to break this down into something that looks like this. X, X, X. We know that this term times this term times this term is 15, but then to make these middle terms appear, if you use guess and check, it could take potentially a really long time. So what we're going to do is learn a shortcut. We don't know, if we set this equal to 0, what the zeros are. And you can't just start testing without a certain guess, without a certain set. If you just start guessing without any sort of prior knowledge, you don't know where to start. You don't know what to test. There's an infinite number of things you could test, so can't really go anywhere. There is a way to generate a list of potential rational zeros. These are numbers that could potentially solve that equation. You generate them by looking at the last term and the leading coefficient. In this case, the leading coefficient is 1, and that will be your friend. The constant in this case, negative 15, is a decent number to work with. You start by taking the last term and listing all the factors of the last term. All of the factors of 15 are 1, 3, 5, and 15. All the factors of 1 are plus or minus 1. You want fewer factors, so the more factors you see, the sadder you are. But just remember, this brings your potential list from infinity to a finite number. So the potential rational zeros, how do you generate it? You pair up all of the possible factors of negative 15 and put them over all the possible factors of the leading coefficient. In this case, we have plus or minus 1, 3, 5, or 15 over plus or minus 1. You'll notice that if that was plus or minus 1 and another number, you would double the number of potential rational zeros. This means that the potential rational zeros are plus or minus 1, 3, 5, and 15. Note, just because these could be rational zeros, they are just potential rational zeros. None of them are guaranteed to work. At this point, you could start plugging in these numbers into our original equation and see which one of them works. Maybe more than one. Hopefully 3. There's a quick way to test them. There's a quick way to evaluate polynomials. This polynomial right here, x cubed plus 7x squared plus 7x minus 15, the way you evaluate a polynomial quickly is you write down the leading coefficients in order. 1, 7, 7, negative 15. If I want to evaluate this polynomial, let's say I wanted to plug in the number 2. What does, if f of x is this, what does f of 2 equal? Well, if I plug in 2, then what you do is you bring down the 1 and you multiply by this number right here. You get 2. You then add, you get 9. You multiply by 2 again, you get 18. You add, you get 25. You multiply, you get 50. And you add together and you get 35. This last number is the answer to this equation. F of 2 is 35. Now you're looking for numbers that make this equal to 0. you are looking for numbers that make that equal to 0. As you found, that's how you simplify your rational functions. So let's test another number, and let's keep it to this list. These are the potential rational zeros. Start with the small positive ones. So the smallest and most positive one, well, most positive, is 1. You write down the same coefficients, 1, 7, 7, and negative 15. You then take the 1. This is the number we're evaluating. So we are evaluating f of 1. What does that equal? Well, this comes down and is 1. You multiply. This is 1. You add. This is 8. You multiply by 1. You get 8. You add. You get 15. You multiply by 1, and you get 15. You add together, and you get 0. That means when you plug in 1 into our equation, into our polynomial right here, you end up with 0. Why is that really helpful? Well, if r is a 0, then x minus r is a factor of the polynomial. Now, it's okay if this doesn't totally make sense, but it means that if a number, when you plug it into a polynomial, equals 0, it means that x minus that number will be a factor. What that means is, if this polynomial right now, we now know if you plug in 1, you get out 0. It means that x minus 1 is a factor of that polynomial. The question is, what's left? What's in here? Well, it turns out it's right in front of you. You see these coefficients? This coefficient is the constant, that's the x, and that's the x squared, and they end up going right there. 1x squared plus 8x plus 15. So we plugged in 1, it came out to be 0, so since 1 was a 0, we knew that x minus 1 had to be a factor. But the key was we needed to know what was left. What else? What times x minus 1 would equal this? Well, it turns out that this is called synthetic division. Synthetic division gives us the coefficients of what's left. What's nice now is that, and I'll pause here for a second just to make this very clear, x minus 1 times x squared plus 8x plus 15. I'm telling you that that's equal to x cubed plus 7x squared plus 7x minus 15. Our goal now is to factor this. But look, we know how to factor that because that's a quadratic. So anytime you see a quadratic, you are home free. And in this case, it is nicely factorable. So we've now factored this, and it turns into that. Now, let's go back. Our original list of zeros, we had 1, 3, 5, 15, negative 1, negative 3, negative 5, and 15. It just happened to be, we got lucky. Our first number we checked came out to be 0. Well, let's say we tested a different one. So we now know that the 3 zeros are, from this right here, we know the zeros are 1, negative 3, and negative 5. Let's hope that that comes out if we tested it first. What would happen if we tested negative 3 first? Well, the coefficients, again, we know what the coefficients are. Here they are. 1, 7, 7, negative 15. 1, 7, 7, negative 15. Let's say we started with, instead of 1, we started with negative 3. You would get 1. You multiply by that, negative 3, you get negative 3. You add, you get 4. Multiply by negative 3, and you get negative 12. Add them together, you get negative 5. Multiply by negative 3, you get 15 and 0. Because we now we know that f of negative 3 is 0, because of that we know that x minus negative 3 is a factor, and what's left here? These coefficients, which are going to be, remember, the constant, the x, and the x squared. So that's x squared plus 4x minus 5. Is this factorable? Well, this turns into x plus 3, and it turns into x plus 5, x minus 1. Does that look familiar? It should. That right there is identical to what we came out to be right here. So are there different orders? Can you test different things in different orders? Absolutely. But the whole point of this is, once we factor, it's much easier to simplify. And if we can simplify, we can generate the vertical asymptotes and the removable discontinuities.